let's talk about Kepler's laws, y'all! Woo! I like to call him Kepler, like the Kepler elf, because it hurts no one and it adds whimsy to my life. You know what? Can't take it away from me. This whole series is on, how knowledge can be more accessible, and what's more accessible than a brand of sweets that is primarily found in those weird vending machines that they keep at zoos. So Kepler had 3 laws of planetary motion. Number 1. Planets orbit in an ellipse. Fancy that. I'm not going to go and explain what an ellipse is because I have another one of those videos in the wheel, so hope you land on it. Though I have yet to make the video, so I don't know if I should vouch for it. Might be trash. Law number 2. Some people call this the equal area and equal time law. The basic rules is that if you have 2 planets that are orbiting one mass, if they have equal area, then they should travel around the mass in equal times. What, Audrey? That's crazy. Hey, no it's not. Simmer down. For example, these 2 ellipses have drastically different axes. As Kepler's second law states, if a planet were to be orbiting around that axis around either axis, it would happen in the same amount of time. This is because as an object is closer to whatever it is orbiting around, it will move faster, and the farther away it is, it'll move slower. So, oh no. So, even though when the object would be right there, it would be moving pretty slow, as it gets closer and closer to the object, it would start moving faster. Wherever an object moves slower is compensated by a place where it would move faster. That isn't needed here because it moves at a constant rate, because this is a perfect circle. As you can tell, I drew a perfect circle, and everyone's gonna tell me I drew a perfect circle because I did a good job drawing a circle. Number 3. I just realized I had my glasses on for the last couple shots, but I'm not reshooting them, so there's just gonna be some continuity errors. Deal with it. So basically, in law number 3 is this formula. Hope future Audrey put that in. The formula states that in a basic orbital pattern, the time that it takes for one object to orbit the central object, squared, is equal to this constant formula times the orbit's semi-major axis cubed. Okay, the m isn't constant because it's the masses put together, but you get it. This is super useful in making satellites. It basically means if you know the weight of your satellite and you know the weight of what you want the satellite to orbit around, then you can figure out the distance that adds up to exactly how long you want the orbit to be. This has been Super Simple Science with Audrey, Kepler's Laws Edition. But it's really